So what I would like to do is just to introduce a little bit into polyhedral model optimizations. What can it be used for? Just to give you a short idea, like polyhedral optimizations for me are just any kind of memory access optimizations. So what we want to do is to look at a piece of a program, look at its memory access pattern and try to optimize that memory access pattern. One way you can optimize it are all those classical loop optimizations, like tiling, interchange, blocking. So those can easily be done in the polyhedral model, but we go beyond that. So we can also detect parallel loops, issue OpenMP parallel code, maybe issue vector instructions. And one area I think is really interesting is actually exposing more parallelism. So we can look at a loop nest, see, okay, it doesn't look parallel, but if we like shift it a little and just do some little transformations, we can actually generate parallel loops. And those parallel loops we can easily then vectorize or OpenMP parallelize. And yeah, I'd like to say, like introduce you a little how we can do this. And the first thing I want like to start is with the polyhedral model. So what the theory behind this. Then I introduce you a little in the research community, which projects exist, what are they doing, and the last thing is, it's actually Poly, so the LLVM part of this. How can we like connect the power of LLVM with the algorithms and the possibilities of research to actually get LLVM some memory optimizations that, yeah, can actually improve performance. So starting looking at the polyhedral model, the first question we ask is, what can we handle? So I call this just like which piece of code can we handle? And we can handle a SCOP, that's a static control part. That's a piece of code where we know where we know everything about the control flow and the memory access at compile time. So we've got three restrictions. First of all, we just want structured control flow. We want for loops and if conditions. But we don't want anything weird like go-tos, exceptions, something like this. And we also don't want to support C++ for construction, like where you can put everything in a for loop. For me, a for loop is just a lower bound, an upper bound, and at every iteration of that for loop, we increment the induction variable by a constant integer. So this is very restrictive. Another restriction that we have is we only allow affine expressions in the loop bounds, in the if conditions, and in the array access functions. So an affine expression is just anything that doesn't have any multiplication. So as soon as you start multiplying a variable with another variable, or a loop induction variable with a parameter, you're not affine anymore. This is not supported in the polyhedral model, so we can approximate in that case. But as long as you want to get the full power of the model, you want to be non-affine. You want to stay affine. So the last thing we want are no side effects. Because we want perfect knowledge about that piece of program, anything that has side effects is accessing memory we don't know about, we don't want in our basic model. Furthermore, in like this very simple definition of a scope, we don't want any point arithmetic and pointer accesses. We just use arrays to access our memory. So this is the very basic model we start with. And there are a lot of extensions, and actually most of these limitations can be removed. But for the introduction part, I just want you to think very simple. And the next thing is, if we have such a very simple piece of code, like two loops, two statements, and some memory accesses, we want to understand how we can translate this in the polyhedral model. So the first thing we need to understand is, in the polyhedral model, we are not thinking anymore about statements. We think about single statement instances. For example, if you start executing that program, the first statement instance that's executed is the blue statement for two specific values of I and j. So for the first loop iteration of the I loop and the j loop, we've got an iteration vector where the I dimension is 1 and the j dimension is also 1. And then if you continue executing the j loop, you get another statement instance with a different iteration vector. And you can continue executing the j loop and finishing this. And after that, we get an instance of the green statement. And continuing the execution of your program, you get a large set of statement instances. And the polyhedral model actually is modeling every single statement instance. So you got a large bunch, like a two-dimensional, one-dimensional vector space, actually two-dimensional just because the blue statement has a two-dimensional iteration space because there are two loops surrounding it. So we have two induction variables that can change in time. And the green statement has a one-dimensional iteration space just because there's only one induction variable that might change. And to simplify the processing of like the big bunch of instances, we just write down the spaces in a very simple manner. We just write down the restrictions on their dimensions. So we got one iteration space, or it's also called domain in the polyhedral model, is like those two restrictions for the blue statement, and there's another domain or iteration space for the green statement. And the next thing we want to know is that the domain or the iteration space itself doesn't contain any information about the execution order of those different instances of a statement. So they can be scheduled arbitrarily. So we need to keep track of the information when are the different statement instances are actually executed. And we store this in a different data structure called the schedule, which actually just maps to every instance of a statement. It maps this instance into a multi-dimensional time. You can think about this multi-dimensional time or clock just like, for example, in this case, we have 3 dimensions, as one dimension being the year of the execution, the next dimension being the day of the execution, and the innermost dimension being the hour of the execution. So you can, as long as you can express this with affine conditions or equalities, you can map those iterations freely in time. And this is actually how you optimize in the polyhedral model. You just look at the program, maybe get a fancy algorithm, and you generate a good schedule for your program. And that schedule defines how the execution order is, and if you are lucky and you got a lot of memory locality, your program is going to be faster. So just by creating schedules, you can do this optimization. You can, like all those classical transformations like tiling, like interchange, can easily be expressed with a schedule, but we can also express transformations that you just cannot express with a set of classical loop transformations. And at that, you can your work is to select the best schedule, but you cannot select all schedules. There are schedules that are not valid. And those schedules are invalid because there are dependencies in your program. So for every, there may be an instance of a statement that is using a value produced by another instance. So we've got a dependency because the instance producing the value needs to be executed before the instance that is using this value. And I've got one example for you where I just created a new schedule that is changing the vector space a little. It's a vector space transformation in mathematics. And I'm not sure if you see this right now, but the interesting thing is the left side of that schedule cannot be executed in parallel because of those dependencies. But the right side, if you look, for example, at the t dimension at the value n, and look at that column of those statement instances, there are no dependencies between those instances for a fixed dimension, for a fixed value of the t dimension. So in that case, we don't have any dependency and can execute those statements in parallel. So if we switch over to code generation, you see the original code, and you see in the transformed code that we introduced a parallel for loop. This is just like where you probably would write an OpenMP parallel, and you're fine. If we are able to generate parallel for loops in the inner level and have some more restrictions satisfied, we can generate vector instructions instead of control flow loops. And this is actually, I think, the most interesting part, and there was a lot of research done in that area, how to generate those parallel loops in the polyhedral model. And this is actually something we don't do yet in Poly, but we've got a lot of research projects, so I'd like to show you a little bit what those projects can achieve. And there are maybe some of you have known them, so there's research since over 20 years, so it's actually very old and still interesting area. So there's been the Swift project close at Stanford, and there was Omega. There's a Lupo project from my university in Passau, and there is the Pluto project from Ohio State. And they did a lot of different stuff. They did tiling, they did pre-vectorization, like preparing the code for vectorization. They did automatic parallelization. Recently, there was some work on CUDA, GPU computation, and even grid computation, really cross-grained parallelism. And they got really nice algorithms that improved performance quite a lot. I want to show you a very simple example. So the simple I can think about is just matrix multiplication. So I run it on my laptop to see how GCC do, how Clang does, and how ICC does. So as most of you know, for high-performance computing, ICC does best. That's obvious. And GCC and Clang don't do that good. But just using Pluto, this is one of those polyhedral tools, to do a source-to-source transformation, we can get GCC and Clang perform almost as good as ICC, which I think is interesting. And something I also thought is really interesting is that we can even improve ICC's performance. Actually double that, for that example, the performance of ICC, which I need to speak about with the ICC guys why this happens. So you see there's you can change performance actually. And I've got another performance number. So this is a recent supercomputing paper, which was accepted, and comparing just more examples if you don't believe that we can do anything except matrix multiplication. So this is compared to ICC minus fast minus parallel, because I didn't even try to compare with GCC or Clang, because they are not yet at a stage of reaching high performance in that area. And for a lot of test cases, we can really change performance of the code that ICC produces. But this is this sounds great, but this is actually just for, cannot be applied on a lot of different programs. And this is why, because Pluto and all those tools are just source-to-source tools. They just work on a very limited subset of C and C++. They require annotated C code. They require very canonical code. So you need to write an affine function in your array access. And which programmer knows about the polyhedral model? Who is going to write his array accesses to match what we expect? So that just doesn't appear very often. And the next thing is, it's probably not really correct, but because just if you think about operator overloading in C++, this is just, it's a research project. They don't think about this implementation details of the C++ standard. So this is where Poly comes into the game. And we are trying to actually bring all this knowledge into LLVM. So what Poly does, it is translating from LLVM IR into a polyhedral representation. It's just starts detecting the interesting parts. The scopes I just presented to you, how they look. We are translating it into a polyhedral model. And if we're really lazy, we just translate it right back, and the program can still be executed. But if we have a little bit more time, we can take a break in the middle and start optimizing that polyhedral representation, start optimizing the memory access patterns. So one way to do it is just import the OpenSCOP description and do it manually. But way more interesting is using one of the existing research tools and make Pluto give us the correct schedule, or a better schedule, to optimize the performance of the program. And as soon as we did some research in that area, we can also start implementing the worthwhile and interesting implementations, optimizations in LLVM or in Poly internally. So we got also a dependency analysis, which I think is one of the most interesting parts, because it's the most detailed dependency analysis I can think of. So if you have time, you should have a look at this one. And following this, what we get is we get a front-end independent, fully automatic way to do polyhedral optimizations, like combining Poly and those tools. And as we are in Poly itself, we can actually issue vector instructions, issue OpenMP function calls, and take advantage of all those transformations. And now I think this is the most interesting part of Poly. I just explained to you that the polyhedral model needs a very strict, needs the program to be very strict in a very specific format. And using LLVM, we don't need most of these restrictions. Like we've got scalar evolution, we've got loop detection, region detection. We've got a lot of canonicalization passes in LLVM. And so, for example, I told you we need structured control flow. I want a certain way to write you the for loop. But if you decide you don't like for loops, you prefer to write your for loop with a goto. Maybe you'd like to use C++ iterators, or you want to write it with a while. As soon as the loop detection can detect the loop and scalar evolution can find a single induction variable, it's the same for us. We're just looking at LLVM IR. There is no difference. So we can get a lot more programs or affine expressions. We don't need the programmer to write an affine expression in an array access. We just need scalar evolution to say this scalar computes a value that is affine, even if it's computed over several loop iterations and doesn't look affine at all. And for example, memory access is only through arrays. There are no arrays in LLVM IR, they're just pointers. So we are not limited to arrays, we can just work on all pointers because we need to do it anyways. And so those are scopes that are completely valid for me. There is no difference in having a very nice formatted code, or we have this a little bit more ugly looking code. So this is something that can very well be optimized by the Polyhedral model. And so I'd like to show you a little bit what's our current status. So all those green little parts is already implemented and works, not for optimizing the Linux kernel probably. I think there are still some bugs left, but like for the test cases we tried, and for the code we're interested in, it works and it's reasonably stable. We are still planning to work on the vectorizer backend, on the OpenMP backend, to actually issue vector instructions. And also like connecting Pluto and POC to do this fully automatically. This is still work in progress. Like I'm working at Ohio State, so they need to adapt POC and Pluto a little bit, but I expect this to be fixed in the next 2 or 3 months probably. And so there are still three interesting open topics in Poly, its core itself. So one of these things are multidimensional arrays, because LLVM IR doesn't have multidimensional arrays. It's linearizing everything. And if you're linearizing a multidimensional array, you're non-affine anymore, which is the case where we need to, where we cannot apply the polyhedral modeling with its full power, but just can get close. So this is limiting the transformations we can apply, and it's also limiting the scopes we can detect. And the next thing is integer modular arithmetics. This is one of the more critical parts because it's actually about correctness, because LLVM IR on integers has all this modulo semantics for all the calculations. And mirroring this in the integer program libraries we are using is needed to prove correctness for any cases. So at the moment, this is not yet completely done, so I'm not, you need a warning. You need a warning in that area that we cannot prove correctness. We are correct, like we generate correct code for all the test cases we use, but this is still one of the areas we are really focusing on to finish in the short time. And the last thing is the code we are generating types that are correct just because they are very large. But often we can use smaller types to do the same thing, so we would like to optimize the size of the types. Because you don't need a 64-bit induction variable if you can prove it's just 8-bit. And this is something we still want to work on. So this is my warning. Poly doesn't have any transformations yet which improve performance. So if you start using Poly and ask me why we don't improve performance, that's probably because it doesn't do it. It's not intended to do it right now. As soon as Pluto is connected, I'm sure we get some performance improvements. And the last thing about correctness. So if you find any transformation which is incorrect, this is probably a bug. You should write it to me. And one thing is, I also didn't explain right here. Here, like we can import a lot of, like we can import a schedule externally. So ask Pluto for a schedule. And one thing we can do with our dependency analysis is we can easily decide if this schedule is correct. So this is not yet implemented, but it's going to be implemented soon. And this is actually one of the steps we're going to take to verify that Poly can generate correct code in any case. And yeah, this is about Poly. So I thank you for listening. I thank Qualcomm for sponsoring me, like getting here. And if you've got any questions, just look at the wiki page at llvm.org about Poly. Thanks, everybody.